and welcome to the chapter about feeding. In this chapter, I will explain the function of a feeder and its different operation modes. Let's start by looking at the feeding process in detail. In this animation, you see a feeding process. The process steps are filling the feeder or the feeder hopper with material from a storage vessel, which happens from the top, and the feeding of the material. The material is conveyed out through the outlet in a continuous manner. For optimal production line operation, the mass flow rate should be as constant as possible. The most commonly used feeder in pharmaceutical manufacturing is the twin screw feeder, which consists of two screws here. In this 2D animation, you can see only one of the screws, so take a look at this video to get a better insight. You see the housing of the two screws and the powder outlet. There are different types of screws, as you can see in this picture. The most suitable screw is chosen depending on the material's physical properties and desired mass flow rate. Following the video, you will find more details about the different screw types. The main process parameter that can be set in a twin screw feeder is the screw speed of the feeding screws, which controls the material flow going out. And with that, we also set the speed of the agitator. This agitator should help to avoid powder bridging in the hopper and helps to get a good filling of the screws. The agitator is often connected to the screw's drive through a gear at a fixed ratio. If this is not the case, the agitator speed is considered a separate process parameter. Additionally, you can set the refill preferences. We will talk more about that in the following video. A feeder can run in two different modes of operation, volumetric mode and gravimetric mode. For the volumetric mode, the screw speed is set to a constant value. This speed has to be priorly determined via calibration runs. Let's look in detail at the volumetric operation. First, the system needs to be calibrated. For calibration, the material fed by the feeder is collected in a vessel for several minutes. The vessel is then weighed with a balance offline. This is repeated for several screw speeds, creating a calibration curve. The desired mass flow rate is then chosen by selecting the screw speed. Here you see a mass flow rate profile that results from a volumetric operation. The red curve shows the screw speed. As you see, it is always the same. The green curve shows the mass flow rate. It is stable for a while and then it goes down over time. Why is that? If we look back at the feeder operation, we see that the fill level decreases over time. This animation is much faster than a real process. In a real process, this emptying phase can take much longer, up to hours, but still it disrupts the mass flow over time. The pressure on the powder just above the screw decreases as the fill level in the hopper decreases. This can lead to lower powder density, or it can also lead to incomplete filling of the screws, even if the agitator is running at an ideal speed. Both effects result in a decrease in mass flow, which is not what we desire in a continuous operation. In gravimetric operation, the feeder mass flow rate is controlled via a feedback control loop based on the weight loss of the system. Here you see the setup for the gravimetric feeding mode. The feeder is placed on a balance. The balance measures the weight loss over time, and this signal allows the controller to adjust the screw speed to reach the desired reference mass flow. These types of feeders are called loss-in-weight feeders. Here you see a diagram of the mass flow in a gravimetric feeder. In green is the mass flow and in red the screw speed. The screw speed increases over time. This counteracts the reduced powder density and possible screw filling problems. Gravimetric feeding has a significant advantage. It enables precise mass flow rate control, but it also comes with its challenges. The feed rate can have a relatively long adjustment period. Even if some feeders allow to set faster reaction times, this can be a challenge. The balance is susceptible to disturbances, like vibrations on the equipment or even people walking by, which can significantly disrupt the control loop. Plus, the feeder needs to be refilled to enable continuous operation. The balance signal is completely disrupted during the refill process, while material is conveyed out. This disrupts the material flow in the hopper and at the same time the control signal. A very challenging situation. Before we go into details on how to overcome this problem, let me make clear that despite these challenges, twin-screw loss-in-weight feeders are always the preferred option in pharmaceutical manufacturing. With that, I'd like to thank you for your attention and see you soon for the video about feeder refill strategies and other feeding issues.